Okay, we're going to start the process of understanding when a series converges and when it diverges by looking at the limit laws for series. So let's suppose we've got one series, the sum of the a's, that does converge, and let's call its limit L. And we've got the sum of the b's, and let's suppose that also converges, and we'll call that the sum of that series M. Then I claim that these three other series, the series you get by adding them up, taking their difference, or taking a multiple of the a's, that these all converge as well. And the reason for this is that let's look at the partial sums. Let's define the s's to be the partial sums of the a's, and we'll define the t's. We need a new variable name because we can't call everything s. We'll call the t's the partial sum of the b's. Now, this statement means that the limit of the s's is L, and this statement means that the limit of the t's is M. So whenever n is large, Sn is very, very close to L, and Tm is very close to M. So if you want to look at the partial sum of AI plus BI, well, that's just the sum of the first A terms plus the sum of the first B terms. That's Sn plus Tn, and that's a number close to L plus a number close to M, and so that gives you a number close to L plus M. You take n larger and larger and larger and larger, and you get closer and closer and closer and closer to L plus M, so the limit is L plus M. The exact same argument works for L minus M. It's just we're taking a number close to L minus a number close to M. And here we're taking a multiple of a number close to L. The exact same arguments work. We've seen this before. This is how we did our limit laws. For functions, this is how we did our limit laws. For sequences, this is how we do our limit laws for series. So for example, suppose somebody gave you the sum of this complicated expression, 1 over n squared plus 2 to the minus n divided by 7. You say, okay, well, I'm just going to use my limit laws on that. That's going to be the sum of 1 over n squared plus the sum of 2 to the minus n over 7. And the sum of 2 to the minus n over 7 is just a seventh of the sum of 2 to the minus n. Now, it's a very deep fact that the sum of 1 over n squared does converge, and in fact it converges to pi squared over 6. And we've already seen that 1/2 plus a quarter plus an eighth plus a 16th and so on, that converges to 1. It's also a geometric series. The first term is a half, and the ratio is a half, so it's 1/2 over 1 minus a half, which is 1. So our answer is pi squared over 6 plus a seventh. The last fact about these series is a criterion for when something doesn't converge. So let's suppose that the series converges. If the series converges, I claim that the individual terms are going to 0. The proof is pretty simple. We take the sum of the first n terms, and that's going to be close to whatever the sum converges to. We take the sum of the first n minus 1 terms, and that's also close to whatever this infinite series is converging to, as long as n is big. We take the difference between them, and everything cancels except the very last term, so we get that the nth partial sum minus the n minus first partial sum is the nth term, and that's a number close to L minus a number close to L, and so that's got to give us a number close to 0. In other words, as n gets bigger and bigger and bigger, an has to get closer and closer and closer to 0. Now, the flip side of that theorem is that if an does not approach 0, so arrow means approach, an arrow with a slash through it means does not approach. If the numbers aren't getting smaller and smaller and smaller, then the sum can't converge and must diverge. So for instance, if you looked at 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on, you don't have to look at all the partial sums. You can say, hey, the terms aren't getting small, so this has to diverge. If you look at 1 plus 2 minus 3 plus 4 and so on, that automatically diverges because the terms aren't getting small. If you look at something like the sum of sine of I, so sine of 1 radian plus sine of 2 radians plus sine of 3 radians, that wanders up and down and up and down, and these terms don't approach zero, so their sum can't converge.